Learning with the Illuminati. Part 5. Introduction to the nerve cell and action potential. The neurons enables communication between different cells and tissues in the body. This through being activated by chemical signals and converting the signal to an electrical signal, which propagates within the nerve cell to finally result in the secretion of chemical substances that can affect the next cell. The electrical signaling. In order to move an electrical signal from the dendrites to the axon terminal, the nerve cell needs to create an electrical charge that can move. This is made possible by the so-called membrane potential, which is a voltage difference across the membrane, or in other words, an electrical difference between the outside and the inside of the cell. The voltage difference is caused by ion pumps, transport proteins, and ion channels. The resting potential is about -65 mV, but can vary between -50 to -90 mV, depending on type of neuron. However, the potential is mostly located closest to the membrane, because the overall charge is more or less neutral, both outside and inside the cell, due to proteins and other molecules that are compensating the charges. The nerve cell goes from being in rest to being in an action potential. When the dendrites receive chemical signals from surrounding neurons, for instance a neurotransmitter that binds to a ligand-gated ion channel and opens it, which causes ions to flow in or out, which changes the electrical potential that are influenced by combinations of the amount of and the individual charges of the ions. The current can either be depolarizing, also known as excitatory, which increases the chance of the nerve cell to be activated further, or the current can be hyperpolarizing, also known as inhibitory, which reduces the chance of further activation. The sum of the depolarizing and hyperpolarizing currents determine if the cell is activated or not. The activation of the cell is called an action potential and is all or nothing. The nerve cell's activational threshold is about -50 mV, but varies between types of cells. The action potential consists of 5 phases. The phases are: resting phase, rising phase, with fast depolarization, overshoot phase, when the membrane is maximally depolarized, falling phase, with fast repolarization, undershoot phase, when the membrane is more negative than the resting potential, also known as hyperpolarized. However, the resting phase generally diminished during repeatedly strong stimuli of the cell. During the resting phase, the cell's voltage-gated potassium channels and voltage-gated sodium channels are closed. At the threshold, which is parallel with the rising phase, the voltage-gated sodium channels opens, letting sodium into the cell, leading to a high influx of sodium ions, which depolarizes the cell. Meanwhile, some of the potassium channels may begin to open slowly, leaking potassium out of the cell. At the overshoot phase, the sodium channels closes, but the potassium channels are still open, causing more potassium to escape to the outside, causing the electrical potential to drop during the falling phase, and eventually hyperpolarizes the cell, causing the undershoot phase, and the channels closes, and the cell pumps ions back to its starting value, often costs ATP. The sodium channels, which are located along the nerve cell, changes its structure in cycles by being activated when the electrical charge changes. Thereafter, the channel blocks itself, causing a refractory period, which prevents the action potential to go backwards. However, due to that the cell has several sodium channels, each in individual stages of the cycle, strong upstream stimuli causes more neurons to fire and more often. causing more excitatory stimuli, which can pressure the cell to start a new wave faster, resulting in more frequent action potentials. The myelin sheath prevents charges to leap over the membrane at areas of the axon, causing faster propagation of the action potential.